I'm here. This is it. Ah, there's the top just there. No, this is fantastic. What a view. I'm back. I was last here 25 years ago. 25 years. And somewhere around here I left my hammer. This is what I remember. This is our ancient heritage laid out before our very eyes.
Scotland's landscape has an epic and violent past. Hidden in these mountains and glens is the history of the planet.
I'm going to show you how this landscape was used by a bunch of brilliant, maverick, eccentric scientists to solve the greatest mysteries of the earth.
And following in the footsteps of these pioneers, who blazed the trail where no one had been before. They showed vision and determination to piece together baffling evidence and uncover the forces that shape our world.
Wow, that's so hot. It's all out there if you know what to look for. Written into the Scottish landscape is the story of the entire planet.
The remote northwest Highlands of Scotland. Ever since people were first drawn to these mountains, they wondered how they were formed. How did they come to be so high, so dramatic? For thousands of years, people believed these were the work of a divine creator. But by the 19th century, a new branch of science had emerged: geology. Scientists began to ask bold new questions about how our Earth was formed. In 1855, a geologist named Roderick Murchison was on his way to the Highlands. Roderick Murchison was an establishment man. He started off in the army, and then he married into money. And it was his wife's suggestion that he took up geology as a more purposeful pursuit than his hobby of fox hunting. Murchison was the most famous geologist of the day. Head of the British Geological Survey, he was an authority throughout the British Empire. And he started the process that led, over the next century, to a true understanding of the way the planet works. Murchison believed that he could explain how the magnificent Scottish landscape had been formed. Murchison has come up with his own grand scheme, which he claims can unlock Scotland's geological past, the story of its landscapes and mountains, and it's based on one very simple idea. The start point for Murchison's grand scheme was very logical. All of Scotland's mountains and landscape were made up of layers of rock, laid one on top of another over time. There was much to be said for this idea. And you can see why if you come to one of the most dramatic and inaccessible landforms in Britain. The Old Man of Storr on the northwest coast of Scotland. First, there's just a small matter of getting to the top.
I dare say that what I'm about to do wouldn't have fazed Murchison at all. But for me, this is a bit of a leap into the blue, really. Literally. Oh,
could possibly go wrong? Ah! Look at this! Woo! Oh, it's quite far, isn't it? Hold on a minute. This may seem rather extreme, but when I get there, this stack will show something very important about how the landscape is formed. Woo! Ah. Final push. Well, here we go, let me touch it. A stack of stone. I'm here. Almost. The sea stack I'm standing on has been scoured by the sea, so that it's completely detached from the headland. And that means it gives this wonderful three-dimensional slice right down through the landscape. Feel as if you're on the top of the world here. As I abseil down this stack, a close look reveals something crucial about the way it was created. These bands of rock around me are like layers on a cake. Murchison and the early geologists recognised that rocks like these started out as soft sediment laid down by water and then solidified, building up one after another over millions of years. So that means that the rocks that are maybe, 20 metres below me are millions of years older than the ones here, and maybe tens of millions of years older than the ones at the top of the stack. This idea of young rock on top of old was the foundation for Murchison's thinking. But he took it much further. As he travelled across Scotland, he saw how exposed rock lay in angled layers. He believed these layers were piled up in a simple pattern, with the oldest rocks on the west of the country and the youngest rocks on the east. For Murchison, it was all so beautifully simple. He was convinced that the Northwest Highlands were built up layer upon layer, just like this stack of slate here. And if you walked inland from west to east, you travelled through a cross-section of younger and younger rocks. Because Murchison was the top dog of geology, for 40 years this grand but simplistic scheme becomes dogma. It was all very logical and plausible, and the evidence seemed to stack up. Murchison was so sure he was right, he used his influence to outmaneuver his rivals and quash any alternative theories. But if only it had been that simple. That mountainside over there seems at first glance to be the perfect example of Murchison's regular succession of layers of rock stacked on top of each other. But actually, the discovery made in the hills around here would shatter that neat little picture. In 1882, a former school teacher came to a wind-blown shepherd's hut overlooking Loch Erible on the very tip of Scotland's north coast. Charles Lapworth was a passionate amateur geologist, modest and self-taught. What he discovered here would demolish Murchison's theory. When Lapworth came here, he stayed in this old shepherd's hut and for weeks braved the elements and went up daily, wandering into the hills to do his work. And the key to the phenomenal success that he had up in those hills was his painstaking methods. He even would wear this special coat, which had all these pockets in it. It's kind of like a portable filing cabinet. And in there he would collect little samples of rocks and samples of fossils and tuck them away. And that allowed him to cover the ground inch by inch, collecting samples as he went in incredible detail, far more detail than that practiced by the so-called expert geologists of the time. Lapworth suspected that Murchison's theory was too simplistic, and he was unwilling to accept the established view. So he set off into the hills in a bid to solve the riddle of the rocks. With little more than a compass and a handful of tools, for 6 weeks he trudged over these hillsides. Rob Butler has been studying the very same mountains around Loch Eriboll for decades.
Do you think Lapworth did this? Woo! I don't know. Do you work in these conditions? It's unbelievable.
Light breeze.
Light breeze. This is the strongest wind I've had.
Well, I've got porridge for breakfast.
It's weighing me down.
Lapworth was driven. He surveyed the landscape in much more detail than the Victorian professionals. And on this cliff face on the flanks of Ben Arnable, he found the evidence that changed our idea of how mountains were formed.
So is this it?
Yeah, this is where Lapworth came.
Fantastic.
Yeah, let's go have a look. Yeah, you can imagine Lapworth coming around here and seeing this place. And he could recognise these should be simply lead, and they should simply go up into younger and younger and younger and younger rock.
Yeah.
And of course that's what Murchison thought, was that it just goes up and up and up. But up there, he went, hang on a minute, yeah, those don't look like younger rocks to me. That stuff is the oldest rocks in Britain. So how could you possibly get the old rocks sitting on top of the young rocks that are down here?
So for people at Murchison, they were quite happy that was just a regular stacked sequence of rocks, but Lapworth could tell that it was wrong.
Yeah, what Lapworth had to sort of establish here was how come you got the older rocks sat on top of the younger? What's going on? That is contact. That's where the action is.
When Lapworth examined the cliff carefully, he spotted something no one had noticed before. A thin layer sandwiched between the old rock above and the young rock below.
What Lapworth recognised was that the old rocks had been reprocessed and ground, rather like a sort of industrial mill, processing and grinding it down into sort of a very streaky looking, smeared out material.
Yeah.
And this is the brilliant bit, because he realised that this processing involves a grinding and therefore a horizontal motion.
This thin streaky layer showed Lapworth something then almost unthinkable. The ancient rocks above had been grinding slowly sideways, up and over the younger rocks below.
So that slab of rock above has been sliding towards us, really. It would have been over our heads, and the bottom of it was all getting crushed along.
Yeah, the old rock started out underneath, so it's been brought up and over and across.
Thrust over.
Murchison had believed the landscape was made up of sedimentary layers that got progressively younger the further east you went. But Lapworth had now discovered evidence that the formation of Scotland's mountains must have been much more violent.
It is a truly revolutionary way of looking at rocks, and the idea that they involve big motions and grinding processes, it does change fundamentally the way in which you view mountains.
Lapworth saw that mountains could be built in a whole new way. The layers of rock didn't follow a simple sequence of youngest rocks on one side of the country and oldest on the other. They could also be thrust up and over each other by massive sideways movements of the earth. This box is a replica of a model that the Victorians used to explain how sideways movements built mountains.
Just putting a layer of black sand on the base of the box here. And that's going to be our first geological layer. Then I'm going to have to get a move on.
These sand layers represent the mountainside behind me.
Now I'll just put the lid on. Now what I'm going to do is turn this wooden handle here, which is going to turn the screw and send these wooden blocks into the layers, as if a great sideways force is crashing in. They do it really slowly though. Here we go. There we go. There she goes, look at that. It actually works. You can see that this slab of rock strata has been thrust up and over on top of this slab of rock strata, which is exactly what Lapworth was saying. Look at it go. Look at it. It's like a bulldozer. It's exactly what it's like. Ah, beautiful. I never thought it'd be this good. Whole series of zigzags form. And what we're doing, most importantly, look behind. We're building mountains. And the point is that is exactly what's going on over there. Get out of here.
What the amateur Lapworth had spotted in the Highlands made a total mockery of Murchison's grand orderly scheme. But for Lapworth, the revelation that vast slabs of rock could move so dramatically left him overwhelmed. Whether it's the excitement of the discovery or the relentless pace of the work, it all proves too much of a strain. Nightmares plague Lapworth. He tosses and turns at night, imagining the weight of great sheets of rock grinding above him. Some say he suffered a nervous breakdown. Lapworth did recover, and he published his findings in 1885. But he was fearful of how his ideas would be received. And for good reason. The geological establishment didn't want to be upstaged by a mere amateur.
There's a final ironic twist to the story. Recognising that trouble was afoot, the Murchison camp sent in their crack team, Ben Peach and John Horn, two of the survey's top geologists that were so good and so inseparable, they were dubbed the Heavenly Twins.
Peach and Horn were a perfect scientific partnership. John Horn was analytical, but Ben Peach was as much an artist as a geologist. His paintings capture brilliantly the structure of rocks and mountains. The Heavenly Twins set off into the Highlands with a very particular mission.
Their job was to kill off the Lapworth idea once and for all. But to their surprise, instead of demonstrating that he was wrong, they proved that Lapworth was dead right.
Peach and Horn found a whole range of mountains in the West Highlands thrust up by big sideways movements. Lapworth was completely vindicated. Although in his lifetime, sadly, he never received the credit his brilliant discovery deserved. The mountains of Scotland had revealed that the world was now more violent than had previously been thought. Rather than a simple build-up of layer upon layer of rock, landscapes were also clearly formed by huge forces that could thrust billions of tons of rock up and over itself. This realization only created fresh puzzles for the men of rock. Where did these massive movements in the earth come from? What could cause solid rock to move sideways so powerfully? The early geologists didn't realise it, but one of the biggest clues was right under their feet. It was lying deep underground in the very same corner of the Scottish Highlands. Just a few miles away from the mountains Lapworth conquered is this dramatic cavern. The mysterious Smoo Caves.
I love exploring caves. You always feel as if you're entering a kind of lost world, really. And for geologists, it's brilliant because they can let you in. You can see the rock in all its glory. This rock's made of limestone. And it's rocks like limestone that can take you to a time and a place. Scotland was very different.
There's a whole swathe of these types of rocks running up and down the West Highlands. What's special about them is something they contain. As Peach and Horn investigated Lapworth's theory, they made an extraordinary discovery of their own.
I know this must look like an overgrown woodlouse, but it's actually a really special fossil, a trilobite. 500 million years or so ago, you'd have found them swimming around in the warm shallows. You get thousands of them all around Scotland, but the ones from this neck of the woods were beautifully drawn by Ben Peach. You can see his sketches here, look at that. Fantastic artist. And he's got this exquisite attention to detail. But even more amazing is the story they tell.
These seemingly insignificant little fossils date back 500 million years. But they're far more than just ancient creatures. They were part of a jigsaw of evidence that would ultimately help to explain the movement of mountains. I'm drawing out a map to show something intriguing about the trilobites. Something that utterly confused Peach and Horn and the other early geologists.
Thing is, it's not the trilobites themselves that were important. It was the type of trilobites and where they were found. The trilobites that were found in England and Wales are the same type that they found right across continental Europe. They were completely different to the trilobites that we found in Scotland. The Scottish ones were the same as those that were found in places like Greenland and Newfoundland down here. In other words, similar to those in North America. The big question was why?
It was a complete mystery. The Victorians came up with all kinds of explanations. One idea was the trilobites had crossed over on a bridge of land between Scotland and North America, which was washed away during the biblical flood. Seems outlandish today, but for Victorian geologists, it was the most plausible explanation they could come up with. Then, another strange piece of the puzzle began to emerge. On December 23rd, 1872, a ship set sail for an epic voyage. A 3-year journey covering 70,000 miles. The HMS Challenger was the first to carry out a survey of the ocean bed. On board was a Scottish scientist, Charles Wyville Thomson, a pioneer of ocean floor exploration. Sailors and scientists knew very little about the depths beneath the waves. Thomson's survey laid the way for the first network of deep-sea telegraph cables and a new era in communications. To survey the seabed, Wyville Thomson's ship had miles and miles of rough hemp rope, at the end of which was a lead weight. Now what they would do is they'd hang this over the edge and just chuck it overboard, really. The lead weight would plunge to the bottom. That was the easy bit. The hard work starts when you're hauling this thing back in. It must have been absolutely hell. I mean, you can imagine doing it when the boat's pitching and tossing. The rope's just slicing through your fingers. It's cold, it's wet, you're miserable, you're exhausted. And all the time you're trying to count the number of fathoms that you're hauling up. And at the end of it all, you've got a single measurement of the depth, and you've got to do that thousands more times. After years of painstaking measurements, Wyville Thomson and his crew located something strange on the Atlantic seabed. Roughly halfway to America, the ocean floor rose sharply. Instead of 5 miles to the bottom of the sea, they discovered it was suddenly less than 2. Wyville Thomson was mystified. At first he thinks he's stumbled upon a submerged mountain, but as the survey progresses, it becomes clear that this is much bigger. A colossal ridge running from one pole to the other, right down the middle of the Atlantic Ocean. Wyville Thomson had discovered not an ancient land bridge between Britain and America, but something even more curious. A chain of underwater mountains that rises from the ocean floor and runs 10,000 miles from the Arctic Sea in the north, down the middle of the Atlantic, almost as far as Antarctica. The origins of this mid-Atlantic ridge were a complete mystery. It was the 20th century before geologists came up with a possible explanation for Lapworth's sideways movements of the Earth, Peachenhorn's isolated trilobites, and Wyville Thomson's mid-Atlantic ridge. The explanation was based on an idea people had spotted as far back as the 1500s, when the first atlases of the globe were drawn. Take a map of the world and cut out the land masses. There we go. There's South America. I'm really not going to do all these islands, just do that. I'm sorry to the northern islands of Canada. They've got to go. When you've cut out all the land masses, you can do this trick of fitting them together. Look, here we go. Here's South America and Africa. We can move them close together. Look at this join here. Look at how just. That's so snug. And then here's little Madagascar. Just tuck it in there. And here's India. You can move India up, and it just tucks in here. And then look, North America, you can just bring down and fit snugly into there. This trick of the maps led some geologists to think that all the world's land masses were once joined together, and that it slowly drifted apart and rearranged themselves over time. An idea they began to call continental drift. Perhaps Wyville Thomson's mid-Atlantic ridge was a giant scar, the crack where this ancient supercontinent had split apart. Continental drift was a very clever theory, but what could cause it to happen? Huge forces were clearly at work, but the men of rock struggled to make sense of their discoveries. Then, early in the 20th century, a gung-ho geologist, again working in Scotland, found another part of the puzzle. The Highlands near Glencoe. For many, a wet and sometimes miserable experience. Back in the early 1900s, an intrepid young geologist, Edward Bailey, had a bracing daily routine out here.
You know, listen, it's going to be cold. It's going to be cold. The boy, it's cold. I knew it was going to be cold. I knew.
Bailey spent years training himself to be tough. As a boy, he invited classmates to slap him in the face to test his endurance. He became a boxing champion. He also slept with his windows wide open in winter. And nothing pleased him more than his daily naked swim.
When I think about Bailey, I'm torn between thinking he's an absolute hero and an absolute nutter. I mean, he used to do this every day. Just dive into some loch or some river. And then he kind of put on his clothes still wet and head off into the mountains. Here's me with all the gear. But that wasn't the style for our Bailey. Look at him. He's got these all-weather shorts. Look at him in the snow. And when the survey told him that wasn't professional enough, he told him to stuff the job. He resigned.
No one could ever argue with Bailey. The shorts stayed on. In 1905, Bailey came to the peaks of Glencoe to join the British Geological Survey team who were mapping the Highlands. What they found was evidence of an explosive era in Scotland's ancient history.
When geologists first started investigating Glencoe, they realised that there were lots of volcanic rocks here. The whole place is stuffed full of them. But they didn't know why. What were they doing here in the heart of the Highlands? Bailey and his team set off to find out.
Inch by inch, they set out to carefully map and survey the landscape. Bailey was often frowned upon, since he took official maps and completely redrew them as he saw fit. He was devoted to his fieldwork in the mountains.
Famously used to eat his lunch straight after his breakfast so he didn't have to carry it. And if his feet got wet while crossing rivers or fords, well, no matter. The holes in his boots let the water drain out. What a guy.
As Bailey climbed through Glencoe, he began to follow a dramatic crack up the side of the mountain. He and his team traced the line across the landscape. and when they drew up their map, it revealed a giant circle. Bailey realised this was no ordinary geological feature. He wondered if it was the mouth of a massive volcano. Then he looked more closely at the rocks themselves.
As Bailey and his team were going along rivers like this, kept on finding two types of rock that had started out as molten magma. One of them is this, it's a granite. You can see it's got really big crystals. The other one is this, look at it. It's got really fine crystals. You can't really see them at all.
Molten rock deep underground cools very slowly, and large crystals have time to grow. But molten rock that is exploded out into open air cools rapidly, so crystals don't have time to form.
So we get one rock that's down deep and the other rock near the surface. Yet here, they're found side by side. Bailey wants to know why.
Then Bailey made a connection. The two rocks and the huge circular crack in the landscape told him he was stood on the remains of a very special kind of volcano. One that would reveal the enormity of the forces that had shaped the continent. I'm going to build a model of how he saw it working.
I know this looks crazy, but I'm making my own wee miniature version of Glencoe. I know this barrel's just got mud and water in it, but to me this is a subterranean pool of molten rock. Magma. It should be red hot, really. And the thing is, this magma is erupting up and spewed out the surface of a volcano. And what I'm going to do is build the top of that volcano.
When volcanoes erupt, the lava and ash builds up, higher and higher, forming a huge heavy cone at the top.
What Bailey realised was that eventually the top of the volcano would get so heavy that the weight of it would sink into the magma below. Ah! Covered in magma. I'm covered. And what would happen is the magma would come rushing out. Ah, let me... Ah. Bailey realises that the volcano is broken along that circular fault line and collapsed violently in on itself, creating the most almighty explosion. And that explains why those two rock types, one at the top of the volcano and the other deep in its roots, are now lying side by side. What Bailey had discovered is a colossal new type of volcano, a caldera.
Calderas produce the most explosive eruptions on Earth. They're a type of mega eruption caused when a volcano collapses in on itself. As the Glencoe volcano erupted, the magma chamber below began to empty. The base could no longer support the top. The heavy upper cone collapsed inwards and caused a catastrophic explosion. Bailey had identified one of the biggest supervolcanoes in Earth's history. For 45 years, he mapped monuments to Scotland's violent volcanic past. He discovered the country was covered in volcanoes. Bailey and his fellow geologists surveyed a great line of them stretching along the islands of the west coast of Scotland. Ardnamurchan, with its perfect ring structure. The cliffs on Egg, solidified sheets of molten rock. And the mighty Cuillin Ridge of Skye. But did Bailey's discoveries have anything to do with trilobites in the mid-Atlantic ridge? Could his discoveries help explain the theory of continental drift? The men of rock now had several pieces of a jigsaw. Lapworth had discovered solid rock had been pushed sideways to form mountain ranges. Peach and Horn had found fossils in Scotland that appeared to match those from the far side of the globe. Bailey had revealed the immeasurable power inside the earth. And Wyville Thomson had uncovered a giant ridge on the seabed. But no one could understand how they were linked. They had observations, but nothing to tie them together. It would take a geological genius to solve the puzzle. I'm at the biggest balloon festival in Britain. Because the theory that united the men of rock's observations came not from studying mountains, but from something much more familiar to us all.
I love watching this, just the effort to get these things off the ground, all the noise, the action, the heat when you get close. And it's a real battle. You can see them fighting with the balloon as if the balloon doesn't really want to go up, but that hot air just keeps on piling in there and then eventually accepts the inevitable and just rears up. And that really is what's driving it there, just hot air. It's pure physics in action.
We all know warm air rises. That's what makes these balloons lift off. It's a simple but fundamental principle of physics. It's called convection. Heat from the burner forms a huge bubble of trapped air inside the balloon. It becomes less dense than the colder air outside. So up it goes. And it's this principle that would turn another man of rock into the unsung hero of geology. Arthur Holmes was one of the most brilliant minds of the 20th century. He was a professor at Edinburgh University, a geologist and a physicist. He was fascinated with the heat deep inside the earth. In 1928, he put forward an extraordinary and controversial idea. That molten rock could behave just like hot air. And perhaps heat, convection, could be driving the movement of the entire surface of the planet over millions of years. I'm meeting geologist John Underhill, who's going to show me how Holmes's ideas work in the lab. First, ice goes under one end of this fish tank.
You just put a couple more in, Ian.
Fine.
Okay, thanks.
At the other end of the tank, John creates a much hotter temperature.
I'm going to slip this heater, a hot plate, underneath this end.
And he's using coloured dyes to track the movement of the water.
So the next thing I've got to do is roll up my sleeves and put the dye into the fish tank.
First, he puts blue dye in the cold end. That's fantastic. In the hot end, he puts red dye. It'll show how heat can create different types of movement. It's quite hypnotic watching it.
Now I see it starting to spread,
Well, you can actually see it starting to go up there.
and this is convection.
Beautiful, isn't it? The hot plate makes the warm red water rise, just like the hot air balloons. On the other side, the cold water is denser, so it sinks. This rise and fall makes something crucial happen.
This is where it gets really interesting, Ian, because it's going to hit the top surface, nowhere to go.
It's going along.
So it's going to now start to go horizontally.
That is gorgeous. And we can see it moving sideways and then actually starting to come down. You can see it starting.
I mean, this is the crucial thing, Ian. We've got horizontal motion of the water column. So a conveyor belt is set up, the cell of convection is set up.
This was Holmes's big breakthrough. The rise and fall of heat drives sideways motion. He realised that if this was molten rock, not water, you'd have a conveyor belt that powered massive movements of the Earth's crust. Now the thing is, we're replicating it in a liquid water, but what Holmes is getting at is that solid Earth actually behaves like a liquid.
Absolutely. I think the key insight that he could bring to all this was he could imagine that actually what we're seeing here happens deep within the Earth, and thereby he was able to recognise the engine that drives continental drift. Now that was revolutionary, that was different, and it was out of kilter. He was considered a maverick for even saying that continental drift was possible.
Holmes sees it clearly. Heat from the inner Earth producing a huge convection cycle, and it's that cycle that moves the continents sideways on the surface of the globe. Now, at last, the jigsaw puzzle was complete. Lapworth's mountain showed how these sideways movements thrust old rocks on top of young. The Glencoe caldera showed where these movements forced the Earth's crust down into the inner Earth. One part of the crust was forced under the other, melting to form a deep pool of molten rock, which burst violently back to the surface. And Wyville-Thomson's Mid-Atlantic Ridge showed where convection pushed the Earth's crust apart, and new rock was forced upwards from beneath. In World War II, Holmes spent many hours on firewood. He had the time to write down everything he knew about geology, and also his most radical ideas. And in 1944, he published his work, The Principles of Physical Geology, which went on to become the single most important geology book of the 20th century. This is actually a big deal for me because this is the original version of Holmes's book. It's fantastic leafing through it. It's great stuff. I mean, this, when it came out, almost immediately made the geologist's bestseller list, and I guess it became kind of our Bible, really. I mean, I had an edition, I think the 5th edition, which got me through university, so it's something that is dear to me. The thing is, Holmes really wrestled with the idea whether to put his theory of convection into this book, and he kind of slides it in at the last minute. It's the very last diagram of the book. There it is. And the point is that this is the first time that convection as a mechanism for moving continents was laid out. You can see here the hot magma rising up as currents, and then moving sideways and then descending back down again. It's interesting here, I just noticed this is to illustrate a purely hypothetical mechanism for engineering continental drift. He's hedging his bets here, he's covering his back. He knows it's controversial, so he's kind of going, well, look, if it did happen, this is one way it might happen. But you get the impression, the very fact that he's got it in there, he knows this is, he really believes in drift, I think. It seemed like the perfect theory. Now all it needed was the proof. It came from a horrifying source. The Cold War brought an unexpected revelation. When a worldwide treaty banned nuclear tests in the atmosphere, bombs were then detonated underground. The Americans needed a method of surveillance to monitor tests around the world. They set up a global network of seismometers to listen in on the tremors on the ground. Then, as they looked for telltale vibrations from enemy nuclear tests, they found something completely unexpected about the structure of the Earth. The seismometers detected not just nuclear tests, but geological events across the world. Volcanic eruptions and earthquakes. Each tremor a pinpoint on a map. Until a pattern emerged. I know it looks a bit psychedelic, but this is the most important recent development in the history of geology. The world map of tectonic plates. It explains how the planet's most devastating events, earthquakes and volcanoes, all lie along plate boundaries. What it really shows is where the geological action is, like over here in the middle of the Atlantic, where two vast slabs of crust are spreading apart. Or over here, along the edge of the Pacific, where two slabs are colliding together. You can see right around the Pacific this so-called ring of fire. All these surface motions are powered by convection from below, just as predicted by Holmes. Heat deep in the Earth has driven our entire geological history. For millions of years, the tectonic plates have moved back and forth across the surface of the planet to create the globe we recognise today. The movement of continents explains the mystery of why fossils from Scotland are so similar to those found thousands of miles away across the ocean. Fossils of Scotland match North America because they were very close together. Scotland was once part of an arc of islands strung out along the edge of a vast continent, Laurentia, with America at its heart. 500 million years ago, Scotland was on the equator and part of an ancient North American continent. Thousands of miles away, separated by a vast ocean, England was part of a different continent too. Over millions of years, those two ancient continents collided. And Scotland finally came together with England in an incredibly slow but immensely powerful act of union. Today, you can still see the results of this great geological clash. These cliffs became crumpled when the two continents collided. They sit on the border between England and Scotland at St Abbs. Layers of rock that were laid down flat on the ocean floor have been thrust up vertically out of the ground. For geologists, it's one of the most remarkable places in the British Isles. God, these rocks are so crumbly, this whole thing. This feels really precarious. Dear. These buckled rocks look as if they've been in some kind of giant pile-up. These ones here are angled in this direction, but just down there, they're angled completely the opposite direction. And it's because this whole coastline is the site of a giant collision, albeit a slow one, between England and Scotland. This clash between the ancient continents forced the rock layers into striking shapes and angles. And it's this collision with England that forced up the mountains of Scotland, fueled volcanic eruptions, and shaped the landscape. Finally, I'm returning to the Scottish mountain where I was inspired to become a geologist, a man of rock. Duncan on the Isle of Raasay, near Skye. This mountaintop's so important to me because it's where I first learned to read the rocks, read the landscape. And the very fact that we can do that today is all down to countless pioneers, amateurs and professionals. People like Lapworth, people like Bailey. It was because of them that we understand Scotland, and through it, the world. Next time, I'll look at the daredevil scientist who revealed that our land had been gripped by a great and ancient ice age. I'm getting squeezed at this moment. And the humble janitor who wondered if the causes of the ice age lay in the heavens. Oh, the sound of the ice age.
Comedy this evening here on BBC HD with Come Fly With Me at 11. But first, we're off to Albert Square. That's next.